All right. Now, my main plan for today is we're going to start chapter 9. This is the last new material before the upcoming test, and it's going to be a short chapter. I plan on only really spending today and Wednesday on it, maybe a tiny bit of Friday, and then we can enter full test review territory. Chapter 9 is going to be about pressure and buoyancy. Pressure being something that most of my students find pretty comfortable given how much it shows up in chemistry. And my plan for today specifically is, for this chapter, I kind of want to run through, do a very cursory look at all the concepts and all the formulas we're going to use, and then practice them a little bit as each one comes up. Wednesday we will practice and familiarize ourselves with all of them more, use them in combinations with each other, and then again Friday we're going to end chapter 9 and move into test review. So today, just looking at all the formulas and all of the concepts for chapter 9 all at once, namely so that you've seen all the formulas and they make more sense during lab this week. Because lab this week is also going to be a buoyancy lab. Any questions or objections to this general plan? All the formulas we're actually going to be looking at are all pretty short, just a couple variables apiece, and they're all going to relate back into each other. The notes I'm also showing today have been added to Brightspace as of this morning, as I realized that my numbering was off from the last couple of years. So chapter 9 is now correctly labeled pressure and buoyant force. Pressure that we're going to be talking about is the same basic pressure that you'll encounter in chemistry, like PV equals nRT measured in pascals. I don't expect that to be very big news. So the main thing that I want to get to today is talking about buoyant force, namely where it comes from and what we do with it. If you're unfamiliar with the word buoyant, that just means floating. So this is the force that causes floating. The same root word as in buoy, like in our harbors. Questions or objections before we get started with this today? Bless you. All right. Now, we're mainly going to be talking about how pressure can be created mostly by fluids and how it then goes on to act upon solids. So states of matter are going to come up mainly as it results to which ones are fluids. So just to remember, liquids and gases both count as fluids. They both exhibit fluid tendencies. They are both able to create pressure on something when an object is submerged in them. They have They have non-definite volume. That's it. Non-definite shape. Sorry. They have non-definite shape. They are able to deform, and something is able to be submerged within them. So both liquids and gases are able to do all of the things we talk about today. Like as of right now, you are submerged in a gas, and so all the stuff we talk about related to being submerged in a fluid applies to you right now in the air. Technically, plasma is also a fluid. I just wouldn't recommend being submerged in it. Additional fun fact, there's a fifth state of matter, if you're unfamiliar with it. I consider it to be the opposite of plasma, because plasma is both common and hot, and Bose-Einstein condensates are cold and so rare you'll never find them, because they exist at absolute zero, and that's just not a thing that happens. So, just to review, the fluid mechanics we discussed refer to both liquids and gases. First two formulas, bless you, density and pressure. Density formulas, same as it's always been, mass over volume. Main things I'll point out are that in this particular course we like kilograms per meters cubed for density, because we like kilograms in meters. Sometimes grams per milliliter might come up, especially in lab this week, since the scales measure grams, and since graduated cylinders tend to have milliliters written on them. But any conversions that are required, I'll make sure are written down. I'll also point out that frustratingly, density's symbol is rho, which is the same as momentum's. Thankfully, the two concepts shouldn't really need to mix in this particular course, other than the fact they'll both be on test 2, but used separately. If it's ever in question what a rho means on your formula sheet, please ask. Next is pressure. The definition of pressure is force over surface area. Anytime pressure is exerted, the object in question is specifically exerting force on the area that it is acting on. So say in chem class, the pressure of a gas inside of a container, that pressure determines the force it exerts over the interior surface area of the container. Also frustratingly, pressure is capital P, which some formula sheets also use for momentum, weirdly. So whichever symbol you like for momentum, there's some conflict here, unfortunately, and I will, again, point out which one's which on your formula sheet if needed. Since we like force in newtons and area in meters squared, we're going to use pascals for pressure around here, just to get the conversion in your notes if you need it. 1 atmospheric pressure, the standard atmospheres that you are used to experiencing, is 101,325 pascals, because 1 pascal is a negligible amount of pressure. 1 meter is not a lot of force, and 1 newton is not a lot of force, and 1 meter squared is a pretty big area for that limited force to be acting in. So I don't know if you could even detect 1 pascal acting on your body. So that's why it takes over 100,000 of them to create air pressure. Questions so far? All right. Quick practice and context building of specifically this formula. If you double the pressure, the force that you exert on something, how does that affect the pressure involved? It's not a trick. Double it. If you double F and keep A the same, pressure gets bigger. Interestingly though, at least I find interestingly, let's say instead you keep force the same, but you cut surface area in half. The same force applied over a smaller area, what happens to pressure? Rises. Yeah. Well, I find this interesting because this is what ties into the human perception of pain. Because it turns out, again, not a biologist, but I've been educated in that, I've been told in that the human nervous system can't detect force, it detects pressure. And that's because every contact force you've ever experienced has been over a surface area. You know, if you put your own hand on your arm, your palm has an area. I don't know the formula for area of palm, but it's there. And the area, in my perspective, the area ends up impacting whether or not something hurts more so than the force. For context, I'm going to take palm and lean against wall. I'm exerting force over the area of my palm, so right now I'm exerting pressure on the wall and it is in turn exerting the same amount of pressure back. I can detect that pressure and right now this feels fine, no discomfort. But let's say I take my hand and I close my fist and I put the flat of my knuckles on the wall, which is at least half the surface area, I think. And you may know from experience, is this more uncomfortable than this? I certainly think so. This is less comfortable, and that's definitely why punches have the capacity to hurt more than slaps. But it hurts even more if I reduce the area from my flat fist to just one finger. And that's why one finger push-ups are near impossible, and ow, that hurts, I quit. So that's like 1/20th the area of even the flat knuckles. So same force the entire time, same force required to hold me up as I lean against the wall, But as the area got smaller and smaller, pain skyrockets because the pressure skyrockets. And pressure is what causes pain, and pressure is also what breaks the skin, because needles, for medical purposes, have a teeny tiny surface area on the very end. And that is why throughout all of human history we have tended to sharpen our weapons, and in modern contexts, our medical equipment. The sharper it is, the smaller the surface area, the more pressure the same force creates. It doesn't take a whole lot of force for a medical needle to be injected. It just has a small surface area. So I found that interesting when I was coming through this class for the first time. Next, once again, that number is the number of pascals the atmospheric air pressure is exerting on your body. And that means that if you know the surface area of your own body, you can find the force the air exerts on your body. My surface area is about 2 meters squared. And so that means that the air is currently crushing me with over 200,000 newtons of force. And thankfully, I don't notice it, because the human body is designed to tune it out. But that is happening to your own body as well. The air is literally crushing you right now, but you're designed around that fact. Your nerves are designed to tune it out, kind of like how you're designed to tune out like the blind spot in your eyes. But furthermore, you don't notice it because all that force is not pushing in one solid direction. The weight of the atmosphere does not just push down on my head, crushing me, because the rule for pressure is it always acts perpendicularly on whatever surface it's touching. And humans have a lot of different angled surfaces. So, all the force is pointing in different directions, so it kind of cancels out. Like, we're still being crushed, but we're not being crushed down and flat. We're being crushed inwards. And we kind of need this because, we're designed to exist in this environment. And I'm under the impression, I know for a fact we have an outward pointing pressure to mitigate this fact. I'm under the impression that comes mostly from your blood flow. Is that right? I think your own blood pressure contributes to the pressure your body exerts out to counteract this inward pointing pressure from the air. And that's why we need Earth's atmosphere to survive outside of just the need to breathe. If you go to space, even if you've got a helmet on, if your bare arm is exposed, it's going to explode. Because it needs that inward pointing pressure to counteract the force that your blood is exerting outward. And that's why in movies, sometimes people explode when they get ejected into space. Don't watch Total Recall. So, I am currently being crushed by this force, and I can't live without it. Questions so far? Just for context building. All right. Next new formula. This is the formula for pressure at a depth within a fluid. P equals density times G times H. And again, you use this to figure out what the pressure is going to be acting on an object based on how deep it is submerged within a fluid of density rho. As this relates to air pressure, just to illustrate, Earth's gravity holds the atmosphere to the Earth, and that's why planets with less gravity tend to have less or no atmosphere. So Earth's gravity is just holding this cloud around us at all times, and at any given moment there's a certain height of it above your head. So the H is height of the column of air all the way up to the edge of the atmosphere. So that column, that air height times average air density times G is where the atmospheric pressure number comes from. This is not the best formula for calculating that though, since the air's density is not constant all the way up. but it illustrates the point, I feel. And it's why as you elevate and H gets smaller, air pressure drops. Likewise, as you say, jump into water and go even deeper down, pressure increases, and then my ears hurt. I'll note though, and you're probably familiar with this as well, when you're underwater, the air pressure is still there. So if you use that formula to calculate water pressure just from water density and water depth alone, that is the additional pressure the water is adding on top of the air pressure that you didn't escape from. So if your head is here, you're still dealing with 101,000 pascals of air pressure, and that only increases as the water adds more as you go deeper. So the formula alone will tell you just water pressure, and if you want to know true pressure, you would add air pressure to whatever you get. So if the homework asks for true pressure at depth within a lake or something, use the formula to find the water pressure, add atmosphere to it. Questions so far? All right. Small bit of practice. We're going to jump to the bottom of a 3-meter deep pool. Namely, specifically, we need to get our head to the bottom of that depth. Because at least as it relates to your ears, it's the depth of your head, not the depth of your feet. Your feet are pretty good at handling pressure, since you're constantly putting your weight on their surface area. Your ears, not so much. So, head is 3 meters beneath the water's surface. Since we like kilograms and meters cubed, water is going to be 1,000 kilograms per meter cubed for the most part in here. So density of fluid times the magnitude of gravity. This is another one of those formulas where we don't care about the negative sign, since pressure acts inwards, not necessarily down. So if it helps on your formula sheet, you can add the absolute value brackets like we do in GPD. And H is depth within the fluid. So 3 meters underwater, head at 3 meters underwater, about 10 feet. You're adding about 29,000 pascals of pressure to your head, which is about a 30% of air pressure. So that deep, you're at 130% pressure, basically. And at least for me, that's the point where it starts getting uncomfortable. Yes?
So when you equalize underwater, how does that work? Like when your ears, I don't know.
When your ears get used to it?
Yeah, sometimes I'll, if I go deep underwater, I'll hold my breath and blow, and my ears, you can hear it.
Right. Sorry, I'm stuck because I don't have a perfect answer for the biology side of that. As it relates to your ears, you do keep air in your ears usually. Your ears are designed to work in air, so there's supposed to be air in there. If you equalize, then the pressure that your body has inside of your ear would have to equal the pressure added from the outside. So I imagine blood flow might increase. It might repressurize the air that it keeps in there. I don't know the exact mechanism, sorry. I know that at least your blood pressure can change as you go deeper. And like there is blood flow to your eardrum, right? So something would have to change. I'm just not 100% sure why. Deep sea divers don't wear helmets anymore, do
You
they?
have to ask Dr. Whitson.
So you go deep diving?
He used to dive for a commercial diver for 7 years.
I did not know that.
Yeah.
I'm sure there's some mechanism. And you'd be more likely to know than me. Yeah, I would guess it, off the top of my head, I'd guess either a change in blood flow or some other mechanism that repressurizes the air that you keep in your ear. Or possibly the drum itself. I think that's the best answer I got for the time being. Okay. So this is additional pressure. If you wanted true pressure, you'd still have to add air pressure to it. But this is additional pressure that your body's not pre-calibrated to deal with, and that's why you have to, as said, equalize down there and pop your ears. But since this is the additional pressure, we can figure out the additional amount of force that would be added to something at the surface area of your eardrum, or your ear canal, I guess, which is very small, surface area of about 7.85 times 10 to the negative fifth meters squared. Oops. Pressure equals force over area. I believe that adds about 2.3 newtons of force into your ear canal, directed in the direction of your eardrum at least. Which might not seem like a lot, but I feel like ears are pretty sensitive, and that's like someone jamming a finger in there. I'd say probably the two most sensitive parts of your body are your eyes and your ears. Does that sound right? And ears are especially sensitive to pressure changes because sound is literally a pressure wave. So it may feel uncomfortable, but that's by design, and without it, you probably wouldn't hear as well. Questions? All right. Last new thing for the day, and then lab and Wednesday we'll review and combine all these things. Buoyant force, so the mechanics of why things float. Buoyant force occurs when something is submerged in a fluid. So we're going to take this box and physically put the whole thing underwater. And buoyant force is caused by a combination of the two main things we've looked at already today. Pressure is force over area, but also P equals density GH, the fact that pressure increases with depth. Since pressure increases with depth, that means the force on the box's surface area is also going to increase with depth. So the lower parts of the box have more force acting on them than the upper parts, even if slightly. Does that make sense? To illustrate that, I'm going to add a bunch of force arrows. The deeper parts of the box, just by virtue of being lower down, have more pressure acting on them, and more pressure will create a greater inward pointing force. So specifically on this cube, since the two vertical sides are totally flat, the inward pointing force lowest will be bigger than the inward pointing force on the upper parts of the sides. Now, that by itself doesn't do much because inward on the left side points to the right, and likewise inward on the right side points to the left. So on a flat cube, these two things just equalize. That's not going to do anything by itself. But technically, the forces are greater on the lower part of it, and that's why, if your feet are on the bottom of the 10-foot pole, you might not notice anything until your head gets to the bottom of the 10-foot pole. But things get, in my opinion, weirder and more interesting when we look at the top of the cube versus the bottom of the cube, because the top and bottom are at single solid depths, right? Flat top, depth doesn't change on the top of the cube, and depth is the same at the bottom of the cube. So the inward pointing arrows on the top are all the same size, unlike the sides. And inward would point down on the top of this flat cube. Now on the bottom of the cube, inward points up, and the bottom is at a greater depth than the top. So the water pressure is greater on the bottom, therefore the inward pointing forces are going to be bigger than the ones at the top pointing down. And if you add all of these force arrows together, the net force from the water pressure points up. The left and right cancel out perfectly, and the upward pointing forces on the bottom are bigger than the downward pointing forces on the top. So the net force points up, and that is the force we call buoyant force. How's that feel? Technically, all fluids do this, and that includes the air that you are currently submerged in. It's just, as it turns out, the strength of the buoyant force depends on the density of the fluid you are submerged in, and air doesn't have much of a density to speak of unless you're a jet and moving fast enough for it to matter. So the air is too thin to create a noticeable buoyant force on your body, but technically, if Earth didn't have an atmosphere, you'd be heavier. You are kind of floating in the air right now, just not a lot. Formula for buoyant force. It's named Archimedes' principle because it stems from that old tale of Archimedes placing a crown in the bathtub and noticing the water level changes because the crown is displacing water. Have you guys heard that story? Oh, weird. I've been saying it all day. I thought that was like, maybe, well, you know what, I'm a physics major, so I've been told it before. But Archimedes, Greek scientist, philosopher, figured out he can use that trick to find the volume of an irregularly sized object. And so that's just where the name comes from. The formula itself says, buoyant force, which is a force, so we're back to measuring things in newtons. Buoyant force is equal to density of the fluid you are submerged in times the volume of the submerged portion of the object times 9.8. If you're on planet Earth. Weirdly, buoyancy does depend on what planet you're on. And like with the other formula or two today that had a G in it, we only care about the magnitude of gravity, not the direction. Specifically because buoyant force always points up. So we definitely don't want to carry through the negative sign on gravity in this one. So just to reiterate again, density, volume, G. Density of the fluid, not of the solid, because the fluid is what's creating the buoyant force. But we do want the volume of the solid because that is the volume of water being pushed out of the way. buoyant force not only is a function of those force arrows from the previous slide, it also has, like, an equally appropriate explanation is when something is underwater, it pushes the water out of the way, the water is pushing back to reclaim its space, and the force is equal to the weight of the water that was displaced. So that's another reason why the G is there. Questions so far? All right. Last bit of practice for the day. We are going to examine a floating block of unknown composition. We don't know what it's made of, but we know it has a volume of 5 meters cubed, and only half of it is under the water. The other half is above the water level. And since we like kilograms per meter cubed, water density will be 1,000. With that factored in, let's determine the buoyant force currently acting on this thing. Water density of 1,000. Now, what should we put in for volume given what I said about how much of it is floating?
3.5, or should we do?
2.5.
Oh, yeah.
Yeah, we cut it in half because only half of it is underwater, only half of it is displacing any water. The half that is above the water is not doing anything to the water itself, therefore the water doesn't directly care. So the magnitude of buoyant force should be about 24,500 newtons up. Buoyant force always points up. Couple small things to note. One, the more volume is underwater, the more buoyant force you generate. When I was a kid, I don't know, I still do it as an adult. Take a beach ball, shove the whole thing under the water, and then let it go, watch it rocket back up. Does that sound familiar? All right. That happens because when the ball is entirely underwater, the volume submerged increases, so the buoyant force increases. And if the buoyant force is way bigger than gravity, the object is just going to fly upwards until they equalize. So if you are trying to float on your back, you're going to sink until enough of you is underwater to generate enough buoyant force to hold you up. It's just a function of whether or not your nose is above the water at that point. Lastly, it is easier to float in more dense materials. Salt water is technically more dense than fresh water, so floating in the ocean is easier, assuming the water isn't choppy. Floating in Salt Lake is even easier. Floating in the Dead Sea is easiest. Not that I'd recommend it, it's gross. Important, but gross. I've heard that the water there's like weirdly thick and uncomfortable because of how salty it is. There are technically fluids that would be even easier to float in. The densest material, the densest fluid is mercury, but I wouldn't recommend that for a different reason. All right, so that's the buoyant force. That always points up. Now my next question is, what must this thing weigh? What is the weight of this cube?
Well, we have force, we have volume. We could use density to find its weight.
Well, we know the volume of the object, but we don't know the object's density. We know the density of the water. We don't know what this thing's made of. There's a trick to this.
We know its surface area, we know its force.
If it's a perfect cube, we can figure out its surface area, you're right. But there's a different trick. There's a different trick that I want to make sure you're familiar with today. what is the net force acting on this object right now, assuming it is stationary floating on the water's surface?
Equilibrium.
It's in equilibrium. If it is stationary, floating, half submerged, net force equals ma. It's not accelerating, therefore net force is 0. What are all the forces on this thing that would need to add up to 0?
Gravity and buoyant pressure.
Gravity and buoyant force. Those are the only two, assuming there isn't like a thruster or a current pushing it side to side or something. If it's just chilling, those should be the only two. And if two things add up to 0, they have a tendency to be equal and opposite. So, if an object is floating in equilibrium, and these are the only two forces, they should be equal and opposite. It's kind of a normal force situation, where if a gravity is sitting still on if an object is sitting still on a surface, gravity and normal force should be equal and opposite. If an object is floating without outside help, its weight should equal the current buoyant force. Now, there are weird fringe scenarios where that might not be true. Like, again, if you are, the beach ball, normally a beach ball is like barely under the water because air is, not very dense. But when you jam the whole thing underwater, there's a third force holding it there, and that is your hands. That would be 3 forces working together in that case. So that's a different scenario. If it's just the 2 and it's floating in place, stationary, they should be equal and opposite. So that is the rule, that is one of the rules for if something floats. If the current buoyant force is less than or greater than its weight. If weight is bigger than buoyant force, you sink, no matter what. You sink until you either hit the bottom or until the water density increases to the point where you can float. If buoyant force is equal to weight, you will float at your current depth. If buoyant force is bigger than weight, you will rocket up until the two equalize. Make sense? So, that would imply that the weight of the that implies that the weight of the object must be negative 24,500 newtons. We can use that to find the mass of the object, and that means we can find the density of the object just to compare it back to water, prove that it should be less dense than water. So Fg equals mg, negative 24,500 equals m times negative 9.8. Cube mass turns out to be about, actually exactly 2,500 kilograms, so about the mass of a truck. However, it might have the mass of the truck. It is much bigger than a truck. Its density is very low compared to water, at least. If we figure out its mass and we know its whole volume, we can find its density. So just to illustrate the point. This cube's mass is 500 kilograms per meter cubed, which is half the density of water, and that's why half of it is above the water's surface. It only needs to submerge half of itself to equalize buoyant force with its own weight. So the other rule that you're probably more familiar with for whether or not something floats is if it is more or less or as dense as the fluid it's trying to float in. If you're less dense, you float. If you're more dense, you sink. That's why whether or not a human floats is kind of random, because every human has different density. Questions, concerns, random thoughts? Excuse me. How do you guys feel about today? I feel like that was a lot of information back to back, but complaints? That's one person. All right. Well, that is all the content from today. Lab this week will be applying all of this, and Wednesday we'll practicing and applying all of this. Specifically, it's a buoyant force lab, so you're going to be taking small objects, measuring if they float, figuring out their submerged volume, calculating buoyant force, and comparing it to weight, things like that. So make sure to bring these notes. And yeah, more practice and stuff on Wednesday. We might talk about one additional thing, but we'll be done by Friday to enter test review. Anyone need anything right now? All right, have a good day. Appreciate you.